with L'Hopital's rule, keep in mind that if it is a free response problem, and the test will have free response problems, you have to write out the entire limit as x approaches infinity for number 15 of natural log x, and write that it is infinity. And also write limit as x approaches infinity of root x, and the fact that it is infinity. And that allows you to go forward and L'Hopital. For multiple choice, though, you don't have to write anything. You can do it in your head if you want and just pick the correct answer. So L'Hopitaling, I am going to take the derivative of just the numerator, the derivative of just the denominator, and the accidental thing that people will do in the middle of a test is quotient rule the thing. Because, you know, when you're taking a test and your brain's all flippity-boo, yeah, it'll do that to you. So if you think about it ahead of time, you're less likely to. And now my job is to rewrite this. So the 1 over x becomes an x in the denominator. Then this 1/2 becomes 2 in the numerator. And this x to the negative 1/2 becomes the square root of x in the numerator. And when I'm simplifying, I still have to write that limit in front. And then I'm going to simplify one more step. And this will be the same thing as 2 over root x. And now I don't have infinity over infinity. And I can logically think through if the denominator is becoming infinitely large while the numerator stays 2, this is heading to 0. And then the problem is done. All right, so that was 15. Now 17. All right, that one, put that one in another color so I keep that up a little bit longer. For number 17, again, if it is free response, you need to write out limit as x approaches 0 of the function. And with natural log x, you want to remember it's heading to negative infinity when you're approaching 0. And then write out limit as x approaches 0. Uh-oh, uh-oh, uh-oh. Good thing we wrote it out. This is not a L'Hopital situation. That means that if my numerator is heading to infinity, whether it be positive or negative, while my denominator is heading to 0, what does that mean the fraction is heading to? Infinity. It's almost like saying double infinity. So the answer to that limit is technically negative infinity, but we would say does not exist. And be forewarned that I'm not against giving you a non-L'Hopitalable limit on a test. Always check. Always check to make sure it's L'Hopitalable. Now, what I realize I never actually went over with you and never videotaped. Why did 17? I'm going to approach it. With number 17, indeterminate forms are if it's 0 over 0 or infinity over infinity. But if you have a mixture with numerator denominator, it's actually like doubly saying either 0 or infinity. So what you want to think about is, let's say I had infinity over 1 as a result of a limit. Do you first of all see that that's going to be heading to infinity? that this is implying infinity. And even if I put negative, that's looking at what happens when the numerator is infinity. If I look at what happens when the denominator is 0, but the numerator is just a nice little pretty 1, that is saying what? So what I want you to first of all see is if you have infinity in the numerator, but a real number in the denominator, that's implying a heading to infinity, be it positive or negative. If you have 0 in the denominator and a real number that isn't 0 in the numerator, you are heading to infinity, be it positive or negative. So in a way, this is saying infinity times infinity, which is actually determinable. They have to tell you the right side of 0, or they will have written the problem improperly. We can only talk about a one-sided limit when it comes to having a one side to your domain. You have to explain it that way. You guys don't have to worry about it, but the problem when it is given to you needs to specify a one-sided limit. And so the answer ends up being does not exist in the long run because it's an infinity and does not exist as just a proper way to answer that limit. Okay. Are we all good? Now, when I come over to these guys, I realize that I never went over with you those other forms. So let me explain this to you. Indeterminate forms of limits. So far we have 0 divided by 0 and infinity divided by infinity, but there are more indeterminate forms than that. Another form is 0 times infinity. And I want to show you that 0 times infinity is actually the same thing as either number 1 or 2, depending on how you look at it. So what I'm going to do is I'm going to write 0 as 0 divided by 1. And I'm going to write infinity as infinity divided by 1. So this is how I'm going to rewrite them. And we're going to look at what is 0 times infinity. 0 is the same thing as 0 over 1. Infinity could be written as infinity over 1. Now, carefully watch. I am allowed to move a fraction to the other side by reciprocating it. In other words, let me say this. If I asked you what is 1 over 1/2, what would you tell me? You would tell me 2. So basically, if I take 2 and I decide that I want it to show up in the denominator, I reciprocate it and put it in the denominator. And I'm going to do that to each of these individually. I'm going to start with this. If I take infinity over 1 and look at its reciprocal and put it in the denominator, I'm not changing the form of this fraction. I'm getting 0 over 1 and 1 over infinity. Now, what is 0 over 1? And I'm loosely putting an equation right here. But what is 0 divided by 1? 0. What is 1 divided by infinity? Also 0. So what I want you to see is if you have 0 times infinity, if you decide to take the infinity and reciprocate it to the denominator, the reciprocal of infinity is 0. And vice versa, I could go the other way if I wanted. I could take 0 times infinity and I could look at writing them as 0 over 1 and infinity over 1. And then choose to reciprocate this one, the 0 over 1, reciprocate that to a denominator. I end up with that infinity over 1 over reciprocate 1 over 0. And then infinity over 1 is infinity. And what's 1 over 0? Also infinity. So what you want to see is if you have multiplication with 0 times infinity, such, now my screen's moving, such as these two problems that I need to move out of the way of the other stuff. Okay, don't move at all. Just that. No. Okay, you want to move everything. How do I tell it to not move everything? All right, maybe I'll just have to recapture it. If you have a situation that is 0 times infinity, you are going to choose which of the two things multiplying is going to reciprocate to the denominator. And depending on the one you choose, you will either create a 0 over 0 or an infinity over infinity. Also know that when you choose which one to change the side of the fraction it's on, you run into the possibility of choosing poorly, shall we say, or choosing the direction that ends up taking you into an infinite L'Hopital loop. That can happen with some of these. And let me re-grab 39. So for this indeterminate form, you want to look at the fact that if x is approaching infinity, this particular factor is infinity. What is the second factor? The second one is heading to 0. I never write out those L'Hopital limits until I am in 0 over 0 or infinity over infinity, because it's a waste of time right now to write it all out. I only have to state these limits right before I use L'Hopital. So you want to just plug it in and in your head realize that you're in an indeterminate form. And every time that happens, you have to rewrite it as a fraction that comes up as one of these two. So who do you want to reciprocate to the denominator? Okay, we will reciprocate x to the denominator. So this limit is equal to the limit as x approaches infinity of, and I'm going to keep the sign of pi over x where it is, but reciprocate x. It's in the denominator, but do you see that I did not change what is there essentially? I already had indeterminate for x equals 0, so. Now, this is the time when on a free response problem, you need to stop and write down the two limits. So limit as x approaches infinity of the sine of pi over x. And you want to be thinking about the fact that this says real number over infinity is going into sine. That means 0 is going into sine. What do I get out? I get 0. Then the denominator's limit and you should see that 1 over infinity means 0. This means you can L'Hopital. So now I L'Hopital, and I take the derivative of just the numerator and write it in the numerator. So derivative of cosine, or I'm ahead of myself. Derivative of sine is cosine, and chain rule says give mommy her baby and multiply by the derivative of the baby. With the derivative of pi over x, it's really pi x to the negative 1. So I'm getting pi times negative 1 over, or negative 1 x to the negative 2. Then I need to take the derivative of just the denominator, and that denominator is x to the negative 1. Its derivative is negative x to the negative 2. And you can write it either way. And now I take a moment to see if this simplifies, because I do have, these are going to cancel each other out. That will leave me with, if I let the positives or the negatives cancel each other out, I now have the limit as x approaches infinity of a lovely pi and a cosine of pi over x. And now I'm ready to think about it again. Here's my x. If I'm plugging in infinity, then pi over infinity is basically heading to 0. What is the cosine of 0? 1. That means we are probably done here. Pi times 1 is pi. Yes, we are done. Woohoo! And just realize that had you chosen differently, had you taken sine and reciprocated it to the denominator, you would have had to take the derivative of cosecant, and it may end up turning out okay. It may turn out really ugly. I'd have to go through it to see. But you can go either way if you end up getting an answer. Now, if I go back to these indeterminate forms, I mentioned so far these 3. There's another form that you should be aware of, and that is specifically positive infinity minus another positive infinity, or it could be negative infinity minus negative infinity, or negative infinity plus positive infinity, if you get the idea of what I'm saying. If it's positive infinity plus positive infinity, that is not indeterminate. If it looks like the infinities are going to subtract each other out, you definitely don't know what's happening, because if one infinity, they could be in a nice ratio with each other, or one of them could be infinitely larger than the other. You have no idea what you're going to get from a subtraction of things that look like they should cancel each other out. I want to also point out to you that in the first 3 indeterminate forms, whether you're dealing with positive or negative on your infinities or on your zeros, it doesn't matter. It's still indeterminate form. But this particular one, the 4th one, it does matter whether it's positive or negative. And I will tell you that every time you run into this, well, not every time, most of the time when you run into this situation, you can see that there's a fraction you can work yourself into and do a common denominator to make it a singleton fraction. You actually will always go to fraction world, but sometimes it's not going to be as obvious as others, but you're not going to run into those problems in this class. So the only other indeterminate forms that are talked about, I never write them down regardless, because they're not even a complete set. The other indeterminate forms that your textbook discusses are exponential indeterminate forms. Come on, come back to me. And so let me just say that there are other indeterminate forms. Ooh, here's my favorite one. People love this one. 1 to the power of infinity. There are several exponential indeterminate forms, and even if you see a list of them in a textbook, it isn't all of them. Do you believe me that 1 to the infinity is not necessarily 1? Here's what I'm not saying. Keep in mind, when I'm talking about these forms, I'm not saying we are getting 0 or we are getting infinity. We are heading to that. So when I say 1 to the infinity power and I say that that is an indeterminate form, I'm not saying that the base is the number 1. I'm saying the base is heading to the number 1. And if you multiply something that is not exactly 1 enough times, you can get something other than 1. I don't go into these forms. It's not on the AP test. Yeah, that's not the reason that I like to give. But anyway, moving on. So this one right here. Let's just take a look at what's going on. If I plug pi over 4 into tangent, what is tangent at pi over 4? 1. So I've got 1 minus 1, I have 0. What is secant doing at pi over 4? Right. Secant is cosine's reciprocal. And what is cosine at pi over 4? I'm so you probably couldn't hear me because my microphone moved. Secant's reciprocal is cosine. And if I plug pi over 4 into cosine, I get root 2 over 2. So this is actually a real number. Oh, wow, that was kind. That means that this is 0. Okay, then let me do some other problems besides L'Hopital. On today's quiz, I just have the fractional version of L'Hopital. I'm not throwing out the special cases. So, okay, 4.5, number 44. Let me find that. All right. I told you with the graphing problems not to worry too much about domain unless you see a logarithm or a square root, and then to just head forward into limits and asymptotes. So with e to the x divided by x, anytime e to the x shows up, you need to turn on your radar for horizontal asymptotes and check the limit as x approaches. Check. The limit as x approaches positive infinity, and the limit as x approaches negative infinity of that function. Also, I need to keep an eye on time. Okay, we're doing all right. Then anytime a denominator shows up, you need to be concerned about horizontal asymptotes, but you also need to look at what makes the denominator 0, and that would be 0. That means we need to take a look at what's happening as x approaches 0 and determine if we have a vertical asymptote or something else. So I start off with e to the x over x. You want to see that that is infinity over infinity. So I'm going to L'Hopital. And now I end up getting infinity out. And when it comes to asymptotes never have, I should say vertical and horizontal asymptotes, never have x heading to negative infinity and the answer heading to infinity. When they both show up, you're dealing with n behavior that heads, up or down. So no horizontal asymptote on the right side, but let's check the left. When I look at the left side, I want to be careful. What does e to the x do when I head to negative infinity instead of heading to positive infinity? Zero. And as far as the domain on this particular equation goes, your exponential function always has a domain of all real numbers. You have a polynomial in the denominator, so the only domain issue is when the denominator is 0. So the domain of this function is going to be everything except x equals 0. And when it comes to domain, you have to be a little bit familiar with the functions that show up, which is why I keep having you graph over and over again. You want to be familiar with these. So coming back to this limit, this is actually 0 over infinity. This is 0. I do have a horizontal asymptote on the left end, but not the right end. Now I need to check out what's happening at 0. So first I think, okay, if I plug 0 in, what's my numerator? E to the 0 is 1, and I have 0 in the denominator. Do you see that that is saying, hey, infinity? But I will say this, if I'm coming in from the right side, then it's positive infinity. If I'm heading from the left side of 0, do you see that that's actually going to be a negative number? Because you'll have a positive numerator, but that denominator is going to be negative if 0 is coming in from the left side. So this actually tells me a bit about my graph. I'm going to draw a vertical asymptote at 0, and then my horizontal asymptote is also 0, but on the left. And with my graph, I know that the right side of 0 goes up, the left side of 0 goes down. And I can also think about the function itself. E to the x is always positive. No matter what I put in, I will only get positive out. Does that tell you a little bit about location? This tells me that when x is positive, I'm going to stay in quadrant 1. But when x is negative, I'm going to be in quadrant 3. But to know a little bit more about what's going on, I need to take the derivative. So low d high minus high d low, square the bottom, and away we go. Anytime you do quotient rule or product rule with an exponential function, you will be able to factor that exponential function out. I will be left with an x minus 1 over x squared. And we're trying to figure out what makes the derivative 0, positive, negative, undefined. So it's important to realize that the range of e to the x will be positive numbers only, never 0. That means if I just need to focus on this other one, it's going to tell me everything. I'm going to make a number line chart for y prime. 0 and 1 are the critical numbers. However, we do see that 0 is actually undefined, so it cannot be a relative minimum or a relative maximum. And then, another thing that'll save me time. My denominator is x squared, always positive. Now I'm just going to say what makes x minus 1 positive versus negative. Do-do-boo, do-do-boo-doo. And if you put together what we have so far, the fact that I have to be in quadrant 3 when x is negative and asymptote to that horizontal asymptote. If I have a negative slope as I go from negative infinity to 0, most likely, what do you think is the concavity? And I'm trying to draw. What would you say is most likely the concavity? Yes, down, most likely. But taking the derivative again, we'll double check that. Then here we can see that we do have a relative minimum. We have the x coordinate. For the y coordinate, we have to go back to the original function and plug it in. When I plug in 1, I'm going to get the number e. So I know that my graph is going to head down until it reaches the point E1, and then it will head up somehow. And if you, yes, dyslexia took over apparently. Oh dear. If you think about how quickly e to the x grows, this is heading up pretty quickly. But I can double check the concavity with the second derivative, but I'm looking at the time and we should probably get the quiz started. Okay, I'm going to stop